So this is lecture 3 today. Again, split into 2 parts like usual, lecture 3A and 3B. At the end of lecture 2, we didn't quite get to doing some linear problem solving. You had some problem solving on your completion assignment today. So we're sort of practicing what would have been ideal to practice on Wednesday, but hopefully if you felt stuck with something, we can reinforce it. Got a quiz next Wednesday at the break. The quiz next Wednesday will be a couple basic problem solving related to sections 1.1 and 1.2. Linear equation problem solving, and then exponential functions and problem solving with exponential functions as well. So let's go ahead and start with some problem solving. Problem solving with linear functions. First one, find an equation of a line passing through the points -2, -5, and 5, 3. What's the first thing to do? Find the slope. The slope, typically written with the letter M. I don't know why, it just is, right? That's the typical letter people use. Is rise over run, delta y over delta x. You don't have to write all these things, but I'm trying to emphasize that they all could be written. And the equation you might have learned in the past might have looked something like this: y2 minus y1 over x2 minus x1, or maybe y1 minus y0 over x1 minus x0. It doesn't matter what you call them. Okay? And in fact, as far as these points go, it doesn't matter which point is the first one and which one is the second one. You should get the same answer either way. Just be consistent. Take the difference of the y-coordinates on the top. So let's take that one to be the first and that one to be the second. y2 would be 3, y1 would be -5. And be careful about signs. 3 minus -5. It's going to be the same as 3 plus 5. 8, right? You got to be careful about signs. The bottom is x2 minus x1, 5 minus -2. 5 minus -2. So we're going to have 8 over 7. 8/7 is the slope. Go ahead and leave it as a fraction, okay, instead of approximating it as a decimal. What's the next thing to do? There's a couple things you can do, actually. Plug in one of these points into what? There's something called the point slope form. There's also slope-intercept form. Did you have a different idea? No? Okay. Point slope form might be written like that. Or maybe your teacher used 1s instead of 0s. Doesn't matter. Or, I actually prefer going ahead and right away adding y0 to both sides. You can also write it like this. Okay, where does this come from? Why is that the equation? Well, it's related to the definition of the slope and the fact that a line has constant slope. Let's go ahead and draw this line here. So it goes through -2, -5. Right about there, and 5, 3. Right about here. You take any point on this line, including one of these 2 points. I guess I am changing my labeling of the points and going from 1s and 2s to 0s here. Okay, I hope you're okay with that. It's not a big deal, as long as you don't let it get you confused. If this is the point x0, y0, you pick an arbitrary point xy, it's still got to satisfy this equation because of the definition of the slope. This equation is equivalent, essentially, to this one with just different symbols. This one is the same as m equals y minus y0 over x minus x0. The same, and this is essentially the same meaning as that, just different symbols. But conceptually speaking, we're thinking of x0, y0 as being some fixed point, and x and y being some arbitrary point. And that's important. They're variable. They're arbitrary. They should work for any point along here. Well, at least in this equation, as long as we're not dividing by 0. Okay? X and Y are variables. So again, it doesn't matter which point you plug in. Let's go ahead and use this form of it. Even though I actually like this form better because it gets you to the function form quicker. One less step. Which point should you pick? It doesn't matter. We'll confirm it won't matter. We'll show that they both get the same answer. So if I pick the first point, its y-coordinate is -5. The slope again was 8/7. The x-coordinate of the first point is -2. This can be simplified to y plus 5 equals 8/7 times x plus 2. We can also distribute the 8/7 through the parentheses if we like and get this. And then we can subtract y from both sides, or 5 from both sides, and get y equals 8/7 x. 5 is 35/7. I'm going to do a calculation in my head here. 16/7 minus 35/7 is -19/7. You should check with me in your own head and make sure you don't make a mistake. Right? I made like 2 or 3 mistakes last lecture. And I had to annotate it on the YouTube video. Let me know if you think I made a mistake. Okay? Look good? Let's confirm we get the same answer with the other point. It doesn't look the same initially. The other point is the point 5, 3. Its y-coordinate is 3. Its x-coordinate is 5. Doesn't look the same. But if you simplify it, solve for y, you will get the same thing. If I haven't made a mistake, at least. 8/7 gets distributed through. 8/7 times -5 is -47. Certainly the slope is the same. Add 3 to both sides. Y will be 8/7 x. 3 is the same as 21/7. 21 minus 40 is -19. Minus 19/7. Same answer. If you get different answers, then you did something wrong somewhere. So maybe that's a encouragement to try it both ways and confirm you get the same answer. That's one way to check your own work. You can also plug in the points into this equation and see that they satisfy the equation. So the slope is 8/7. The y-intercept is -19/7, which is a little bit higher than -3. So this graph is not perfect. It looks like I made it go through -3 there. It's actually a little bit higher. Something about more like that. -19/7 is the y-intercept. Second problem, which we're going to go quicker through these. Find an equation of the line parallel to the line number 1, going through a different point, 4, 7. Parallel means they have the same slope. So you can go ahead and use the same slope of 8/7. And let me go ahead and use the second form, because it's one less step. And that's, again, the form I usually prefer using. Because I usually want to solve for y as a function of x anyway. 8/7 going to the point 4, 7. Like that. Another nice thing about this form of it is you can see quickly that when x is 4, y is 7, right? Plug in x equals 4 there, you get 0. 0 plus 7 is 7. You can very quickly see that it does pass through the right point. Expand. Simplify. Y is 8/7 x plus 17/7. That would be a line parallel to the original with the slope of it, because it's got the same slope, but a different y-intercept, a larger, higher y-intercept. It's going to be higher than that other line over there. Look good? No mistakes? Okay. Find to leave things as fractions. By the way, if you multiply both sides by 7, you still get an equation for the line that doesn't involve any fractions. It's just not solved for y as a function of x, but it still is an equation of the line. The points in the line still satisfy this equation, make both sides equal to each other when you plug the numbers. How about perpendicular? How do I make a line that's perpendicular? Opposite reciprocal. What's an opposite reciprocal? You're right. That's the slope. Well, but it's an opposite reciprocal of 8/7. What's that? Negative 7/8. Right. Goes to the same 0.47, so go ahead and just subtract 4 inside there and add 7 outside there. Okay. And if you don't have to simplify, you're actually done. Okay. But we usually like simplifying. 7/8 gets distributed through the parentheses. Negative 7/8 times negative 4 will be plus. 4 will cancel with 8. 7/2. 7 is the same as 14 over 7. It looks like, if I have not made a mistake, that's this for the answer. So that would be a line through the same point, 4, 7, perpendicular to that other line. I won't bother drawing it. Okay? You should be able to draw it. Find the slope-intercept form of the formula for a linear function with rate of change negative 3 and y-intercept y equals 4. That's a really easy problem, isn't it? You don't even have to really do any work, right? The rate of change is the same as the slope. That's the only thing to realize here. The rate of change is the same as the slope. Negative 3x plus 4 is going to be the answer, and you can call this f of x. F of x if you like. Probably would have been good for me to do that there. Right, y equals f of x equals that.
I just have a question for the last one. You
Uh-huh.
did the 3. Why did you put the 7 as the B? Or like,
Right there?
yeah.
Why did I do that? Because it was going to the 0.47.
But that's why. Right?
Yep. Which is what you want.
Okay, so,
When x is 4, you get 0 here, 0 plus 7 is 7. So it's going to go to the 0.47.
but, okay, I'm good.
Okay, maybe at the break we'll take a look
Okay.
at it? Okay. Remind me. Here's a practical question. The cost to make 0 shirts at a factory is $1,000. Wait, why would we make 0 shirts? Well, we wouldn't make 0 shirts if we wanted to actually own a factory and make shirts. But you could say, well, if we did own this factory, and we did happen to make 0 shirts, maybe our workers went on strike or something, then we'd have a cost still because we'd still have to heat the factory or something, or we'd still have electricity paid for. Maybe this is over a certain amount of time, maybe even over a day, or even an hour if it's a really huge factory. Though we're not referring to the time. For every shirt made, the cost is $12. How much does it cost to make 123 shirts? Also, how many shirts can be made for $3,940? Now, I hope you look at this and say to yourself, I can answer these questions without any equations. Because it's true, you can answer them without equations. The first question could be answered by saying, okay, I guess there's a $1,000 cost. That's the cost of heating and electricity or whatever, plus the cost for every shirt. 123 shirts times $12. It's really dollars per shirt. You only see dollars here, but it does say for every shirt made, the cost is $12. So in terms of the equation, calculation we do, we really should think of it as dollars per shirt. And the shirts then will cancel, leaving you an answer finally in dollars. That would be an ideal way to show you work. If you do this, 123 times 12 is 1476. Add 1,000, you're going to get $2,476. Okay? No variables there, just do a calculation. And I hope it makes intuitive sense that to answer the second question, how many shirts can be sold, can be made for this much cost? I hope it makes intuitive sense that you should first subtract off the fixed cost for making 0 shirts, and then just divide by 12. 3940 minus 1,000 divided by $12 per shirt would be a way to show your work. So that's $29.40 divided by $12 per shirt. The dollars are going to cancel, thinking in terms of units, and your final units will be in shirts. Because when you're dividing by something that's 1 over shirts, it's really the same as having shirts at the top. You can multiply the top and the bottom of this fraction by shirts, if you like. Anyway, this comes out to be a fairly nice number here. 29.40 divided by 12 is 245 shirts. Again, don't worry in the units about changing between singular and plural. That's not a big deal. You just do whatever is appropriate. Okay. We could use functions here, by the way, as well. And you should be able to use functions if I ask you to. And you should be able to graph it and think about it in terms of the graph. That's really what's going to be most helpful for calculus. If y is the cost and x is the number of shirts made, y is c of x. C is the name of the function, but I'm using the letter c because it kind of emphasizes it's a cost. The intercept is the 1,000. That's the amount to pay when you make x equals 0 shirts plus 12x. This is in dollars. The 12 is in dollars per shirt. The x is in shirts. That's the function you use to solve the problem if you want to use a function. And in part B, what you're doing is you're really solving for when that function equals 200 or equals 3940. You really can think of part B this way, and this kind of work shows you that you do the exact same calculations as before, though not including the units until the very end. And I'm usually okay with not including the units until the very end, though sometimes it's helpful to go and include them in the middle. Okay, so you can use a function. Graphically, what's going on here? We've got y-intercept of 1,000. We are interested in when this gets up to 3940. Say up here. I didn't draw this perfectly to scale. The value of x we just found is the 245. We also, in the first part of the problem, figured out what the output is when the input is 123. We found it to be 2476. So you should be able to translate back and forth between the numbers and the graph too. Understand what graphs mean. So if that's not clear, that's something to work on. All right, now we're talking generalities. First of all, just reinforcing what we just talked about with equations of lines. Well, there's something called the standard form, which can be written in either of these ways. I actually looked this up online, and some people write it like that, and some people write it like that. By the way, don't be bothered by the D there. I could have used the C. I chose to use the D instead of the C in the second one because if I take this one and write it that way, technically the D would equal negative C. So that's why I chose a different letter. Again, the letters you use don't matter. It's the idea that's important. A, B, and C are constants, or A, B, and D are constants. These true forms are typically called the standard form. Sometimes you see equations of lines written like one of those ways, and you want to write it in some other form, like slope-intercept form. That's the most common way to write it, as a function of x, like that. And then there's finally, again, the point-slope form. Either one of these is okay. I typically prefer the second one because if I want to solve for y as a function of x, it's already done. I don't have to bother adding y0 to both sides. All right, we are now about to move on to exponential functions. Exponential functions, in some ways, are not that much more difficult than linear functions. But in other ways, they're really a lot more difficult. It's kind of weird. that way. Here we go. First, why are they important? They're still relatively simple. They're simpler than trig functions, you might say, in some respects, though in other respects they're of similar difficulty. Initially, you were going to think about them in a simple way. This is going to get harder, though, as we go. Whereas linear functions have a constant rate of change, exponential functions have a constant relative, or percent, rate of change. So maybe clearest initially if you think about it in terms of an example with a table of values. I'm going to use the letters L of x and E of x to emphasize a linear function and an exponential function. Let's pick values of x that do not go up by 1. Let's pick something different, like 2. And we won't even start at x equals 0, we'll start at x equals 3, say. Let's have both of these functions have the same output when x is 3, maybe 6. But then let's make this one a linear function and this one exponential. How? Since x keeps going up by the same amount every time, in this case you keep adding by 2. For the linear function, you want to keep adding the same amount, not necessarily 2, but the same amount. Let's pick 5. If I keep adding 5 to those outputs, that will then be a linear function. If you graph these points, this is the x's, this is the y's, you'll get points in a straight line with a slope of 5, actually. If, on the other hand, I keep multiplying by the same number, say 5, that'll be an exponential function. Multiply by 5, 6 times 5 is 30. 30 times 5 is 150. 150 times 5 is 750. Right, double check. Yeah, okay. That's an exponential function. Here we kept, so we're, in both cases, we keep adding the same number to the input of the function. For the linear function, we keep adding the same number as well, but it can be a different number. However, for the exponential function, we keep multiplying by the same number. That's the most basic thing to realize, and that means it's a constant percent rate of change. The percent's pretty big here, although, for every 2 units, we are multiplying by 5, which is really 400% growth. If you multiply by 2, it's 100% growth. If you multiply by 3, it's 200% growth. If you multiply by 4, it's 300% growth. If you multiply by 5, it's 400% growth. Right? That makes more sense to think about the doubling. Doubling is 100% growth. This is 400% growth each time. As x increases by 2 each time. It would be less growth if x increases by 1. That's a constant relative rate of change. Linear functions, as I just mentioned, are built from adding and subtracting. I could have subtracted instead of added. I could have subtracted 5 each time. Exponential functions are built from multiplying and dividing. Instead of multiplying by 5, I could have divided by 5. Because that's really the same as multiplying, right? Isn't dividing the same as multiplying? How? Multiplying by the reciprocal. If I divide by 5 each time, that's the same as multiplying by 1/5. Right? Fundamental idea about fractions. They have many applications. Population growth, radioactive decay, heating and cooling. These are just some of the more common applications. There's hundreds or even thousands more. Compound interest in financial math in general. Economic growth is kind of financial math in general. Probability and statistics, they come up. There's something called an exponential distribution, which I probably will talk about at some point this semester. We are doing some data modeling sometimes. And they often arise as part of solutions of what are called differential equations, which is related to calculus. And we have a whole class of differential equations here at Bethel. In fact, right after this class, I teach a class called Differential Equations with Linear Algebra. So it's a pretty important subject. It's got applications all over the place in science. And exponential functions arise very often as part of solutions of differential equations. Here's some details. General formula. Initially, it's simplest to think of it this way. Initially. But we're not always going to write it that way. In fact, usually we will not. But initially, it's simplest to think of it this way. Y equals f of x equals a times b to the x. A can be anything, though you wouldn't typically want it to be 0 because then it's really just a 0 function. B can be any positive number, except we don't typically think 3, 1. I probably should have added in A is not 0 here as well. A is called the initial value. If you imagine x to be time, though if x were time, you typically use the letter t instead. It's the value of the function when x is 0. B is called the base sometimes, or it's also called the growth/decay factor. It's related to how the function grows or decays in a special way that we'll see. Fundamental property number 1, again, A is the initial value. It is the output of the function when the input is 0. That's very easy to verify. Just plug in. B to the 0 is 1, so it simplifies to A. Is anything to the 0 power 1? Almost. Technically, 0 to the 0 power is not 1. Does anybody know what 0 to the 0 power is equal to? If this is a trick question. 0 to the 0 power doesn't equal anything. It's undefined. I think we'll be able to see why 0 to the 0 is left undefined later in the semester. We should be able to see that. Fundamental property number 2. As I already mentioned at the top, B is the growth/decay factor. If you want to be a little bit more precise with respect to x, or y with respect to x, here's an example of what it means. For instance, for every 1 unit that x increases, y gets multiplied by b. Just like here, analogous to here, for every 2 units x increased, y got multiplied by 5. Similar kind of property. Not the exact same, but they're related. Let's think about it in the abstract. If I increase x by 1 unit, what happens? Look at that. And there's a property of exponents. Here's where your placement/skills test exam skills come in handy. When you got to a situation like that, that's the same as this. Right? Usually you think about going the other direction, right? Usually if you got something like this, you add the exponents. We can go back the other way too whenever it's helpful. Here's a situation where it's helpful to think about it this way. B to the first is b. This is the same as this. In other words, it's the same as b times f of x. Adding 1 to the input makes the output get multiplied by b. You should be able to think about why that's the case based on this kind of calculation. What I'm about to show you is a similar calculation, then we'll take our break. What if the change in x is not 1, but delta x? I could do a very similar thing that I did over here, except use a delta x instead of a 1. What would happen if we did that? You get b to the x times f of x at the end instead of b to the first. like with this table, really looking here, delta x is 2 each time. 5, I'm multiplying by 5 each time, that must evidently be b squared for this table, for this exponential function. So b for this exponential function must be the square root of 5, which you wouldn't know necessarily just by thinking about it right away, at least. Since this must be b squared because x keeps going up by 2, 5 is b squared, so b must be the square root of 5. You can also divide both sides of this equation by f of x. And what you're seeing is this ratio for an exponential function is, at least if delta x is fixed, like 1 or 2 or whatever, is a constant, no matter what x is. That's special for exponential functions. Doesn't happen with other functions. And also, if you want to get a little bit more complicated about it, this sort of emphasizes that this is really the relative rate of change. That's the amount the function changes right there. This is the starting value of the function when the input is x. So the fraction really represents the percent change, at least as a decimal without a percent sign. And you can check this calculation. You get b to the delta x minus 1. So for example, if delta x is 1, which is the most common thing to think about here, this is b minus 1. So as in this one, if b is square root of 5, well, what is that? It's about 2 point what? 2, 3? Somebody do that quick on their calculator? I should know this. 2.23. Then b minus 1 is 1.23. As a percent, that's 123%. Right? Yeah. So for every 2 units increase in x, the growth is 400%. For every 1 unit, the growth is 123%. It would more than double as x went from 3 to 4, for example. It would go from 6 up to something bigger than 12, maybe 14 or 15 or something. All right, let's take a break.